When the circuit shown above is connected, the capacitor is uncharged and switch S is open. The switch is then closed, and after a short time there's a current of 62.5 milliamps in the capacitor branch. What is the current through the 200 ohm resistor at that instant? So I'm going to give everybody names because I like to name things. So I'm going to call this the EMF. I'm going to call this R1. I'm going to call this R2. And I call this, this is going to be the capacitor C. We're going to call this the current through the capacitor. I'm going to change colors because I want to be consistent. So this is the capacitor. I don't care that's a bad color because I'm not going to see it anymore. But its current is I capacitance. And if we look at the way the battery is flowing, well, I guess they tell us the current's running that way. So we also assume that this current is running that way. I'm going to call that I2. And this is going to be I1. And then I'm going to start taking some loops. So let's take this loop first. Start at the back of the battery, go up and go through R2 and then that way. In that case, we get the EMF as we start the battery. Then so we're doing this. We go EMF, we gain the battery's EMF, we go around, we lose the resistor's potential. So that's obviously I2, R2. And then we lose the 100 resistor as well. So that's I1, R1. And Kirchhoff tells us that that's 0. On the other hand, I can also use something like this, going around here and then back through that resistor. In that case, I gain the battery, but I lose the voltage on the capacitor. And then I lose I1, R1. And again, complete loop, so we get 0. And then we have that this current, which is IC, plus this current, which is I2, they meet at this junction, and then I1 leaves that junction. So the junction rule tells us that I1 equals I2 plus IC. And then we start going variable hunting. How many variables do we actually have in this equation? Well, what do we not know? We don't know I2, that's what we're looking for. And we don't know I1 because we weren't given it. So let's go up here and say, well, we don't know that, and we don't know that, and we don't know that. And we don't know the voltage across the capacitor, and we weren't given the capacitance, so it's hard to measure. So there we go. How many things is that? Well, we don't know I2, we don't know I1, we don't know, V across the capacitor. On the other hand, how many equations do we have? Well, 1, 2, 3. So 3 unknowns, 3 equations. We expect there to be a solution. Actually, a little bit stronger than that, we can also just consider this equation and this equation. That's only 2 equations, but in those 2 equations, I have only 2 unknowns. So I fully expect that that would be enough to get everything done. So cleaning things up and having a quick recap, we have these 2 equations, we have these 2 unknowns. It's not a good color for that, so let's do this. This unknown and this unknown. And so we expect a solution. Probably the best thing is to eliminate I1. So we go back to this first equation and we say the EMF minus I2R2 minus, and now we know that I1 is I2 plus the capacitor current times R1 has to be 0. We're looking for I2, so let's, I'm going to distribute because I can't do it in my head without hurting myself. And then let's bring I2s over to their own side. So we have, we're left with the EMF minus I capacitor times R1 on one side, and I2 R2 plus I2 R1 on the other side, which of course I'm going to factor out as I2 times the sum of the resistors, which gives me that I2 should be the EMF minus the current through the capacitor times the resistor 1 over the sum of the resistors. Grinding out all those numbers, we get 0.0125 amps, which is 12.5 milliamps. And happily, that is in fact the answer that was also on AP Classroom. So a little bit grungy, but not terrible.